Hello. Today we'll talk about conditional statements. It may sound complicated, but the fact is you've probably known about conditional statements all your life and used them. Things like, if tomorrow was a school day, then I should set my alarm. If tomorrow is Thursday, I won't eat in the cafeteria. If tomorrow is Thursday, they serve split pea soup. I don't like split pea soup. If tomorrow is Thursday, then I won't eat in the cafeteria. You've been doing this all your life. Now we're just putting a name to it to help you get confused. So you thought what you were doing was simple. It's actually very complicated. And we're going to do that right now. Make it real complicated for you. No, it's not that bad. You get an if-then statement, right? Like you say, if today's Sunday, then tomorrow is Monday. Real simple. All you have to do is identify. The part after the if, that's the hypothesis. The part after the then, that would be the ending, that's the conclusion. Kind of makes sense, right? Now, if then, that's a common way to say it in English, but this is a math class, and we use shorthand, don't we? So, P implies Q is another way of saying the same thing. This little line right here, arrow, says the same thing as if P then Q. P implies Q. Same thing. Suppose you want to say today is not Sunday. Well, that's real easy in mathematics. Put this little squiggle in front of it so you could write Sunday. That's Sunday. On the other hand, that is not Sunday. Save you writing a few letters. Put that little squiggle in front of it. That means not. So, one of the first things we can do with a conditional statement is scramble it. We start out with the standard conditional. If P, then Q. That's simple enough. What would be the converse of that? Well, just flip them around. The conclusion becomes the hypothesis. The hypothesis becomes the conclusion. If it's Sunday, then it's Monday. You can switch it around to, it is Monday, then yesterday was Sunday. The inverse, that's when you negate both of them. If today is not Sunday, then tomorrow is not Monday. That would work. Contrapositive, well, that's where you flip it and take the inverse. In other words, it's the converse of the inverse, or the inverse of the converse. And this has nothing to do with the tennis shoe here. This is just a form of conditional or logical statement. This is the converse of the conditional, the inverse of the conditional, and the contrapositive of the conditional. There's not much you can do with these but memorize them. There's no particular reason why this is called the converse that I know of for inverse. And if there is, it probably wouldn't help you remember it anyway. So we just got some more of that tough vocabulary to remember. Sorry. Now the conditional and the converse, they have kind of a special relationship. For instance, I could write this as, just to make it simpler, P implies Q. I can do that with all of them. What the heck? This says that Q implies P. This says not P implies not Q. And this says not Q implies not P. Now these two here, they're kind of important. Because if this is true, and this is true, if it works both ways, then we can write this is one of the shorthand notations for a bicondition. The long way of writing it is P if and only if Q. If both of these are true, we write this as a biconditional. We write it P if and only if Q, or P-I-F-F-Q as a shorthand for if and only if, or the shorter shorthand is just the arrow going both ways, which is also the symbol we used for a line. When you put it in between P and Q, it doesn't mean line, it means biconditional. And this is an extremely important type of condition, meaning that it goes both ways. Now there is a way of looking at this that makes it easy to avoid confusion, or at least helps to avoid confusion, if we use something called a Venn diagram, which you've probably seen before. And now let's introduce something that should make it a little bit easier to evaluate these expressions when we get to the point where we need to do that. That's called a Venn diagram. One of the simplest ways to draw it is just any kind of a closed curve. It doesn't have to be a circle or a perfect oval or anything like that. It's just something that's closed. And we'll say that this is P here. All of this has the quality P. And this end here has the quality of Q. So everything that's in Q must be in P, because we drew it that way. That's what that's telling you. On the other hand, let's write it this way. P implies Q. Would that be true? If you're inside this large circle, do you have to be inside this small circle? Nope. That would be false. What about the converse? Q implies P. With respect to a Venn diagram, that's the same as saying, if I am inside this set, must I be inside this one? And the answer is yes. So this part is true. So how do you get a biconditional to be true? Well, the Venn diagram for that would look like this. And then there's another one. And they coincide completely. So that P and Q would, taken as two sets, would in a sense be right on top of each other, so to speak. In other words, there is no overlap. There's nothing outside of Q that would be P, and there's nothing outside of P that would be Q. So, mostly just a bunch of new words here. We've got the if P then Q, hypothesis, conclusion. We have all these permutations of the conditional statement. And then we have this extremely important variation, the biconditional here, which means that the implication goes both ways. Then we have some choices of notation also, or if P then Q, or P implies Q. It's also something called a truth table, which we will get into more of later on, but the way that usually works is something like this, standard table. And here we have something called a truth table. It's a way to organize what the heck's going on, especially with more complicated expressions. Here we have our P and our Q, not P, not Q, and then our conditional and our permutations on the conditional. And over here we have the converse. This is the inverse. And here's the contrapositive. Notice the truth values of these two line up, they're the same. And the truth values of these two line up, and they're the same. You may have noticed something else here that looks kind of weird. P is false, Q is true, and the expression evaluates is true. Why in the world would that be? Well, if you start with a false hypothesis, then anything is true. If the average man is 10 feet tall, then I am from Mars. That's a true statement. Why? Well, you start with if the average man is 8 feet tall. Well, that's not true. So anything can follow from something that's not true. You could look at it that way. If the hypothesis isn't true, then you can make up anything. If 2 equals 3, then there are 8 days in the week. Well, there's a certain sense to that, because if 2 did equal 3, maybe there would be 8 days in the week. Who knows? When you start with an hypothesis that isn't true, then in a sense all bets are off, and you're always going to get a value of truth. And that means that even when the conclusion is false, if the hypothesis is false, it's still going to evaluate as true. That's a weird little aspect of logic, and the reason for it lies in something called Boolean algebra, because you can assign numbers to these two things, a 1 and a 0, sorry, and then create an algebra with just those two numbers. It's kind of weird. You'd have things like 1 plus 1 equals 0, and it gets strange. But it's called a logical calculus, so to speak. And it's how computers work. They only know zeros and ones, true and false, and they take it from there. And they get a lot done. So Boolean algebra with nothing but zeros and ones does sound kind of silly and pointless, but in fact, it's very powerful and you get a lot done with it. And that's the reason for odd things like a false hypothesis always leads to a true conditional. It's the way the zeros and ones work out. Your arithmetic gets all messed up if you don't do it that way. And there's a certain sense to it. I mean, like I said, if you're going to assume something that isn't true, then what follows could be anything. Yeah, I know, philosophically that's a little unsatisfying, but it's just the way it is. Let's take a look at some problems. This stuff should make a lot more sense when you watch it actually happen. And here's one of those someone made a mistake, what was it problems. This one, I think it's probably easiest just to draw a diagram that shows what's going on. All high school students take 4 English courses. So we take the property of 4 English courses, draw a big circle there, and inside that we put high school student, because all high school students take 4 English courses. Now, there are other people who may take 4 English courses, college students, people who aren't even in school who just want to take English courses, people taking English as a second language. Lots of people take English courses. They're not always high school students, but if they are high school students, they must take 4 English courses. Now there's another bigger category out here, which is the category of 4 courses. If a student takes, or anybody takes 4 English courses, is he inside the category of people who take 4 courses? Yes, he is. However, if a person takes 4 courses, must they be English? No. 4 courses is a bigger containment here. So you can take 4 courses without taking English courses. So this part here, this doesn't follow. That's false. That's really all you had to do. You just draw yourself a diagram of what's contained in what, or what may be overlapping. You've got containment, and then there are also cases where you have intersections. In this case, containment and intersection are actually kind of the same thing. This means that all of it intersects with this. If I drew it differently, this wouldn't be right, but if I went like that and the high school students were here, that would be an intersection. But this would be the intersection, and this would be outside the intersection. This belongs to both sets. This doesn't. Here, the entire set is the intersection, because the property of high school student belongs to both sets, both high school student and 4 English courses. But not the other way around. The property of 4 English courses does not necessarily imply high school student. And the property of 4 courses does not necessarily imply 4 English courses. There's several problems which illustrate the fact that all definitions can be written as biconditional statements. In other words, they're all if and only if statements. Or they can't be anyway. This one, an angle with measure between 90 and 180 is called obtuse. You can rewrite that as an angle is obtuse if and only if the angle measure is between 90 and 180. Simple. 2 angles are a linear pair if they are adjacent angles whose non-common sides are opposite rays. 2 angles are a linear pair if and only if they are adjacent angles, blah blah blah, just like it says here. This is fairly easy. Coplanar points. Points that lie in the same plane. Rewrite that as points are coplanar if and only if they lie in the same plane. See? It's pretty easy. The main thing to remember off of this is that all definitions can be written as biconditionals. All definitions are really if and only if statements. And here's one. And get some practice in writing the converse. Remember what the converse is? Let's see here. I think it's up here. Or reverse. The hypothesis and the conclusion. That sounds easy enough. Let's see here. If x is less than 4, then x is greater than 0. If x is greater than 0, then x is greater than 4. We could use a Venn diagram. We could just look at it, or actually a number line kind of works for that. It's kind of like a Venn diagram in this case. Let's put 0 right here, and 4 is over here, right? Now, if we are greater than 0, that means we're off to the left of 0. Is 4 to the left of 0? Oh yes, it is. Now, if x is greater than 0, is it greater than 4? Well, no, there's a whole bunch of stuff in here that's greater than 0, but it's not to the right of 4. So, the converse is false. What about this one? X is less than 6. Well, let's see. The converse would be if minus x is greater than minus 6. Let's try the implication symbol this time. That implies that x is less than 6. Well, I would say that's true. Wait a minute. Oh, that's a... That one goes the wrong way, pardon me. probably true, but just by using rules of algebra, when you multiply by a negative number, you can reverse sign. But there's another way we could look at it using the sets that we brought up before. We could look at it this way. There's 6, there's 0, and here's minus 6, okay? Now, if x is minus x, there we go, lies over here. Minus x is all on this side. Well, that's going to mean that minus 6, since it has a minimum over here, that is, not minus 6, x has a minimum over here. Just the minimum is minus 6, which means over here the maximum is going to be plus 6, and it goes down from there. So, if minus x is greater than minus 6, meaning minus x is over here, then x is over here. And that is in fact less than 6, isn't it? So, this one, the converse, is true. What about this? Well, the converse would be x less than or equal to 0 implies x is less than or equal to minus x. Once again, we can draw ourselves a diagram. Here's the number line. Here is the new hypothesis, because we're working with the converse now. X is less than or equal to 0. X is way off to the left here. Well, then where's minus x? Well, minus x would have to be way over here, wouldn't it? We're just reversing everything. If x was positive, minus x would be negative. Since x is negative, minus x is positive. So minus x is a positive number and x is a negative number. Positive numbers are greater than negative numbers. And since the possibility of 0, they included the endpoints, and x could be equal to 0, but they accounted for that in the or equal to part. So the statement is true. Pardon me. Now here's something, well, let's see here. I don't think we need all of this. No, we just need this part here. Let's say that our data points are x1, x2, dot, 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 x sub n. Don't know how many there are yet. x1 is the minimum. X sub n is the maximum. Well, first, let's see if the mean would be greater than the minimum. There's only one thing we need to add to this statement before we get started. X and Y are the least and greatest values in your data set. Well, suppose X and Y are the same number. We didn't say that there are more than 2 values in the data set, and we did not say that X and Y are distinct. Maybe you only measured 2 people. Maybe you only got 2 people in your class. I actually saw a class once that only had 1 person in it. I forget what it was called. That was one highly underworked teacher. So we're going to assume that this is true. None of these data points are equal. It just makes it easier. If they are, it works out the same. Well, if there's only 2 and they're equal, then it turns out that the statement isn't true, because the mean is just the number. For instance, if the number was 6 foot even, and then 6 foot even? Well, the mean would be 6 foot even, and that's not between 6 foot, is it? You only got one real number. So we'll have to pretend that they're distinct. Now, how do we get the mean? Well, we add up the numbers, and we divide by how many numbers there are. In this case, we would add these up and then divide by n. Well, what about the first two? x1 plus x2. Well, if we start with x2 greater than x1, I can put that up here. Add the same thing to both sides. That doesn't change the inequality, does it? We got an x1 here and an x1 here. That's exactly what I've got here. So, this quantity is larger than this. Now we can just group this. Again, we've got that this is greater than this, so I can add x1 over here. Over here I can add any number x1 or greater, and it'll still be greater, right? So if I add x3 over here, which is greater, and x1 over here, or if you like it better, I could write this way. x3 is greater than x1. Now I can add these up into here without affecting the inequality. Why? Because x3 is greater than x1. So the inequality still holds if I add this over here and this here. If x3 were equal to x1, this inequality would still hold. Adding equals to each side doesn't change it. So if I add something that's even greater than x1 over here, that definitely will maintain the inequality. Now, thinking back to previous lecture where we had pattern recognition, do you see a pattern here? I do. I bet you do too. As we keep adding these points, they're always going to be greater than this side over here, where we're just adding the same point. Why in the world would I do that? Well, eventually, on this side, we're going to end up with x1 plus x2 x sub n, and we want the mean. So we're going to divide by n. And let me get rid of this stuff here. It's kind of in the way. And I just use the word kind of. When I'm done, I'll find myself $20 and hit myself in the back of the head. I don't like that expression. Kind of, sort of. Extremely imprecise ways of speaking. That, we've just divided by n on both sides. Same as multiplying through by 1 over n. You can do the same on both sides. This x1, x1, we're going to end up with n of these x1s here. So that's n times x1. And we divided by n. Which means that our mean here must be greater than x1. These two n's cancel. We just end up with x1. We can make exactly the same argument, just reversing everything, with the maximum value here. Here, x sub n. Everything will be reversed, and in the end, no surprise, we will get that this number here is less than x sub n. And we'll have that the mean is between the maximum and the minimum. Write the converse of the statement. Aha. Now, if the mean lies between x and y, let's just write x sub m for mean, and let's say that it's greater than, let's not use that. Let's say it's greater than some number z and less than some number y. The converse of this would be if the mean is between x and y, between y and z, then y and z must be the minimum and maximum of the data set. And that is entirely incorrect. I mean, just pick an example. Remember, counter examples are all you need to prove that something's not true. Now we could have data sets along some number line here. Put our mean here, and we got points here, 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 here. Here's the minimum and the maximum, but the mean lies between these 2 points too. That's not the maximum, that's not the minimum. It lies between these 2 points. You can pick lots of points between which the mean will lie, and they are not going to be the minimum or the maximum in general. Minimum and maximums are possibilities for those points, but they aren't necessarily those points. Now for the last one down here, you kind of have to remember what these things mean. Mean, median, and mode. Remember mean, that's where you add them all up and then divide by however many you had. The median, that's, if you remember percentiles, that is the 0.5 percentile. That is the point at which half the values lie above it and half the values lie below it. This may not be part of your data set. The mode? Well, the mode is the most frequently occurring value. So that value has to be in the data set. So the mode will always be one of your measurements. That's what makes this statement true. And here's one where we're going to go the other direction. Usually we use Venn diagrams to give ourselves a visual representation of what's going on with conditional statements. In this case, we're going to start with the diagram and see what kind of a conditional statement we can get out of it. Naturally, we can get more than one. They want a statement that uses, it says, between the various groups, which I assume means they want us to include all three. That means that, well, we'll just look at this. Jazz band is included in band. So, wouldn't it be true that jazz band implies band? If someone's in the jazz band, they must be in the band. However, band does not imply jazz band. They could be out here in a band, but not in the jazz band. But we didn't use chorus. However, suppose I join these. If I write jazz band, actually I wouldn't even need to, would I? Jazz band implies band. And band implies not chorus. They can't be in both, can they? Or, another conditional we could write is not chorus implies not band. But, since, pardon me, implies not band, and not jazz band. You can do it that way, I guess. You can get lots of statements out of this. Now I was trying to find a way to get all three of them in there. That's one, I guess. That little conjunctive there, looks kind of like an A. Makes it easy to remember. That just means and. You'll see another one later. Upside down means or. That means or. but we're not using that right now. This one means and. It's like an A, but without the cross piece there. This one we can do pretty quick, I'd say. If we rearrange this, we should get x squared minus x minus 12. Oh, got it. Equals 0. Now we have our standard quadratic, and we can factor this. We need factors of 12 that add up to minus 1, which would be minus 4 and 3. So we get x plus 4 times obviously I reversed the signs here. It's x minus 4 times x plus 3, which means 4 is definitely a root, but then seems to me x equals 4 or minus 3. So the way I look at it, this isn't quite true anyway. But if we reverse it, we take the converse. If x equals 4, let's just write it out. X equals 4 implies that this, or the other version, x minus 10 equals x plus 2. This one here is definitely true. Can it be combined to form a true biconditional? Well, that's the funny thing, because the converse is true, but the other isn't. So I would say no, you really can't form this into a true biconditional, because x could also equal minus 3. When you write if and only if, that means both sets coincide, and they don't. We have a minus 3 here that lies outside our conclusion. Well, that's our quick introduction to what conditionals are. As I probably mentioned, there's not much you can do with this stuff other than memorize it. Sorry, I can't give you an easy way to do it. There's no formula you can use. Just kind of have to memorize it, I guess. Oh, God, I said kind of again. There, I just smacked myself in the head. You just have to memorize it. There's no kind of about it. You definitely, absolutely, and do need to memorize this. Other than that, it should be fairly easy, and we're going to use more of these. You'll see a lot more conditionals. And through the repetition, it'll become much easier. So don't be intimidated that this looks like really hardcore logic stuff. It's not that bad.